Hi, I am Jack's astronaut Koichi Wakata. Welcome to Story Time from Space.
You're not real. You're not real.
What? You are? Is any of it real? I mean, look at this. Look at it! A world built on fantasy, hypnotizing us into the biggest slumber mankind has ever seen. Real? You want to talk about reality? Dig pretty deep, kiddo, before you can find anything real. We live in a kingdom of bullshit.
Mission Control, this is the International Space Station.
Peter, good to see you. Hey, welcome aboard, everybody. Welcome to our little zero-G fantasy land. Welcome to our little zero-G fantasy land. Welcome to our little zero-G fantasy land.
Yeah, we can play Scrabble in space. Just keep it velcroed to the wall or the ceiling.
Please welcome the Retired Liars.
Expedition 5 was a busy mission and we accomplished a lot. We conducted over 20 different experiments.
Here I have a single graviton that's floating free in the cabin and it's spinning. You can see it wants to spin. I can't make it tip over. It's stable about the axis I let it go in. The spin axis is up and down.
Just goes around, doesn't go straight. Just sort of floating around. I'm throwing the paper boomerang, and we'll see what happens. We'll watch it again. And boy, look how fast that travels across the spaceship. It really surprised me. We'll watch it.
This should be a graphic demonstration of a spinning and a non-spinning graviton. You see the spinning graviton stays stable while you see that one is spinning and one is not. And the one that's not spinning just tumbles free while the other one maintains the orientation I let it go in.
The racquetball has less mass than the pool ball, and as a result, it will always travel faster than the pool ball, even if I throw the pool ball at the racquetball. Now if I tape the two of them together and again hit the racquetball with another pool ball, you'll see it curves around the pool ball.
Boy, that thing shot up like a rocket, and that caught me by surprise. I didn't expect that in this microgravity environment that it would go up to that.
I was playing with the clacker balls one afternoon on the shuttle, and I had let them go and they drifted apart and they did this funny motion. So what I tried to do was get that funny motion to repeat itself. I experimented a little bit. I tried various different actions by spinning them in one direction. Before flight, I had to practice with the clacker balls a bit since I had never played with them before. I became quite proficient at using the clacker balls.
Now here I have a curious combination of two gravitons that are attached together on a wiffle ball. And I have them both spinning in the same direction. So spinning opposite directions cancel each other, orthogonal to each other. That is, their alignment to each other. And I'm going to spin them all in the same direction with reference to their attachment to the wiffle ball.
This ball and cup was one of the more difficult. You can see that the ball just won't stay in the cup as it does on Earth. Of course, on Earth we have gravity holding the ball in the cup. When I put the ball in the cup and then push to hold it, I actually pushed the ball away. So I never could get the ball to stay inside the cup. We'll try again. I just push on the ball and that pushes the ball out again.
I try to throw this ping pong ball the old-fashioned way, but it doesn't curve down toward the target like I would expect on Earth. And then I attempt to throw another ball with some twist to see if it changes the direction of the ball. Now one thing you'll have to remember is that the Velcro of the ball does have to touch the target. Let me try this again. And then I'll throw it one more time with some spin.
Getting the car to run on the track was a bit easier in space than on Earth because the car didn't have to build up as much velocity to stay on the track as it did on Earth.
Here's an experiment, a good demonstration of how a non-spinning graviton behaves just like a ball on the end of a string. I can change the axis of rotation just like you could with anything attached to a string. Once I spin this graviton, look how it maintains that stability around its rotation axis. I can spin it around and around, and it wants to stay in an orientation that to spin it.
As you can see, that without the effect of gravity, the shoe just bounces off. The shoe right at the pole, I'm going to use a spinning motion to see if I can catch the pole. At this point, the shoe is pretty stable in a spinning motion around the pole. Without the effect of gravity, it doesn't slow down and settle at the bottom of the pole.
One of the things that's always impressed me here on Earth was the ability of the professional basketball players to spin around and make these really neat moves. Well, I was trying some of that in space.
We had this thing floating around, but without the effect of gravity, it just doesn't work the same way.
That's a funny looking snake-like thing. Had a big kick out of seeing that. How they reacted when we spun them around.
And it doesn't matter whether I hold the rod up or whether I hold it down, because in this microgravity environment, there is no up and down.
I think between the 130 different experiments we're running all around the laboratories, the chance for board games and space darts, and now space curveball, there's never any shortage of things to do here on the International Space Station.
Thank you for listening here on Story Time from Space.